we are going to start 24 and 25, chapter 24 and 25. It's about magnets and magnetic and, electromagnetic induction. So today we'll just kind of cover what is a magnet, what's a magnetic field, and how is it linked to electricity. So magnets have two poles. They always have two poles. You can think of them as the negative and positive charges from the last chapter. So like the negative charge would be the south pole and the positive charge would be the north pole. Like poles repel and opposites attract, just like with charges. Things that are attracted to magnets and can become magnets or magnetized are iron, nickel, and cobalt. And there's a couple of other things that can do it too. The neodymium-1, stuff like that. Some compound stuff. And magnets have magnetic fields, which are very similar to electric fields. The same rules for field lines apply as they did to electric fields. And I can show you that here. I actually have a fancy thing. And just spread it around so you can see it. And this is just a fluid with iron filings in it. And it's got like a little bar that goes in there and spreads it around. All right. So here is a magnet. Not sure if you can see the iron filings kind of lining up around the edge there. So these iron filings actually line up with that magnetic field. And I've got a bar magnet. You see how the iron filings line up at the poles for the most part, and when it's around the sides, you can see it kind of go sideways, like right here and right here. And you're welcome to come look at this in class. Actually, probably keep it. I don't know. I have a better plan. Let's do this. Let's see if this works. All right, here we go. Maybe not. Like this? Like this? No, it doesn't want to work. Did I ruin it? There you go. So you can see mostly at the poles here, and then when it's on this side, they're all lined up along the magnetic field lines. So when we draw them, we use them as representations to draw these fields, but they really truly are there. They're just invisible. Let's see if I can do it with another one. This one. So you can see that it's all attracted to it. Move the magnet out of the way. So, there you go. So you can see the spot. Okay. I don't have any other fun shapes. I don't see any cups, so fly right through these things before you can write them down. No. Okay, here we go. Magnetic domains. This is what makes up a magnet. This is why something is magnetic. And a magnetic domain is made up of electrons all in the same orientation direction. So electrons, they spin around and they kind of orbit-ish the nucleus. And if you can get them all to spin in the same direction and kind of orbit in the same direction, then their own personal magnetic fields start to add up and build on each other until they get strong enough that they're actually affecting more than just what's in the atom. So you can create a very strong magnetic field this way. The more electrons you have in that same spin or that same orientation, the stronger the magnetic field. Now, if you heat up a magnet or if you drop a magnet, it makes these electrons spin in different ways. So whenever I throw this magnet, it gets weaker because it's knocking the electrons off of their spin. Or if I were to heat it up, it's going to make it weaker. Now, if I wanted to make this stronger, I would put this magnet in a nice, strong magnetic field. I would heat it up, and I would leave it in that orientation that I wanted it, and it would cool. And it's going to match whatever magnetic field it's in. So those iron electrons, they all line up in the same direction, and that is what's going to create this magnetic field. So if I cool this in the Earth's magnetic field, then whichever way is north, that way, right, will be this direction. So all these electrons are going to line up so that that way is north, even though that way is actually south. Now, I can magnify something temporarily. For instance, I have this paper clip, and let me show you that. Here's another paper clip, right? Not magnetic. Now, I can make it magnetic by putting it into a magnetic field. Let's put it this way, and I just moving it around inside the same field in the same orientation, trying to get those electrons, the ones that are kind of loose, all in that same direction. So let's see if I can magnetize. Now, it would be easier if I had a stronger magnet. This is not a very good magnet. Now, where's mine? Now, it doesn't work for very long. So I can magnetize it. And it is actually magnetic. Now, it's not very strong, so it doesn't work very well. But it does work. Questions? I swear I'm not a wizard. I just have some, I have this one on the board. Let's try that one. Although I don't know if it's circle that will work. This one. Oh, that worked a little better. I could cheat. No, it's just not holding it very well. Oh, so you good with this slide? Okay. Okay, these are magnetic domains. You can see that the electrons all kind of point in the same direction, and in this one they're all aligned in the same direction. So when they're all lined up in the same direction, each electron has its own magnetic field. So all these magnetic fields of these electrons are getting bigger and bigger and bigger, so they can actually extend pretty far outside the atom. Now in this one, this is what just a normal material would look like when it's not magnetized. You can see that the electrons, even though they have an electric field, they're all pointing in different directions. So they actually end up canceling their magnetic fields out. And that's why, like this piece of paper, is not magnetized. And that is why only a couple of different materials can become magnetized, because they have the electrons that can change their orientation and stay that. All right, electromagnetism. Electricity and magnetism actually go hand in hand. There were two people that kind of discovered this at the same time, Faraday and Henry. I don't remember their first names, but those are the big scientists. Michael Faraday, and I can't remember the other guy's. His last name is Henry. What they found is that when they put electricity through a wire, so they just had a wire, and they put a compass near it, the compass would either be towards the wire or deflected away from the wire, and it always happened at 90 degrees. So one of Faraday's laws is saying that your electricity is always going to be, your electric field is always going to be 90 to a magnetic field. So anytime you have an electric current, you're going to have a magnetic field. And that magnetic field is always going to be 90 degrees to it. So you can see I have some lovely pictures up here, which I actually have to redraw since they won't be on the e-beam. And I got schooled on how to draw an arrow. So we'll redraw that here, and I'll try to, yeah. So let's say that this is your wire. It's a nice big long wire. And your current is going that direction in the wire. If this is true, there's a right-hand rule that you can use. There's a couple of different right-hand rules. They use 4 different ones in your book, and they all kind of say the same thing. They're just for specific situations. So for this one, for the wire, what you want to do is grab the wire with the direction, with your thumb in the direction of the current. So if we reached out and grabbed this wire, and make sure you use your right hand, not the left one, right hand, and put your thumb in the direction of the wire, you can see that the magnetic field actually comes towards you. So it's coming at you. I can't draw it like that. I'm sorry, guys. This direction. At you. There you go. I hope that helps. And this is your magnetic field. It is around the wire, but coming at you. So you always want to look at the top of the wire when you answer these questions. They'll be like, is it going towards you? Is it going away from you? Is it coming, at you? So always look at the top. So in this question, we would say it is coming at, it's going towards us. So your thumb is in this direction, and your fingers crawl or curve towards you. This is one of the right-hand rules. Again, there's 4 of them. The other one is pretty much the same thing, except for you use your finger as the magnetic field, and then your index finger as the force. And we'll talk about that one tomorrow. Now, B is the magnetic field, in case you're wondering why I wrote a B there. I is current, and B is magnetic field. Why does the up work, but the down doesn't? It's very strange. There. So using this right-hand rule, if the wire is coming at you, which direction is the magnetic field going to be moving? It's coming at you. Which direction is the magnetic field moving? Or, direction. What's the direction of the magnet? It's not necessarily moving. So take your right hand out. Come on, I don't see, one person's doing it. He's got it right. Take your right hand out. Now, the current's coming towards you, so point your thumb at you. And your fingers are kind of going this direction. So around the wire, they'd be going counterclockwise. So your answer for this would be counterclockwise. Now, if it's going away from you, what's it look like? Clockwise, right. It's going this way. Or to the right is fine. Clockwise. Okay, now, if the magnetic field is spinning clockwise, which way is the current going to be going? Away from you, and that means that this one must be towards you. Okay, not that hard. Okay, we can create an electromagnet. Now, you can do this at home and really impress your 5-year-old sister, right? All you need is a nail and a piece of wire. This is a piece of copper wire. I think I stole it from something that goes to something in my garage. I don't know. Anyways, it's insulated, and I had to strip the end, so this is just the copper is exposed. And on the inside is an iron nail. You want to make sure you get an iron nail and not like an aluminum nail or one of those weird ones. So this is just an iron nail. I can make the electromagnetic stronger by wrapping more coils around it. And notice that none of them overlap. They're all right next to each other. This is called a solenoid. All right, and then over here I have a battery. Any battery will work. AA will work. This is just my little 6-volt battery here. And connect the 2 ends. Now, it does get a little hot, so I try not to touch it when I do this, which makes it kind of difficult when I'm trying to pick up magnets. So here you go. Now this, as long as your battery is charged, will become a magnet. And the stronger your battery, the more it's going to pick up. The more coils you have on the nail, the more it's going to pick up. And then as soon as you let it go, it's no longer a magnet. So that's how to create a nice little electromagnet for you. And the Earth is actually a giant magnet. We think that the reason the Earth is a giant magnet is because we have a solid nickel core, I think it's nickel, surrounded by a molten, iron mess. And it's molten. So as the Earth spins, and that creates a very, very strong magnetic field. So if this is the Earth, this is about how far the Earth's magnetic field extends. Now, if there was no solar wind, which there is a lot of solar wind, and that solar wind kind of drags our magnetic field back, but if there wasn't solar wind, it would be a nice, beautiful sphere like we normally would see. But the solar wind drags it back. And sometimes it's so strong that it actually pushes this magnetic field back so that our atmosphere is exposed. And when that happens, it strips particles off of our atmosphere. Now, this is kind of what happened to Mars. We think that Mars got hit with a very huge asteroid, and it kind of messed up the internal workings of Mars. So Mars doesn't have a liquid core anymore, and that's why it doesn't have a very strong magnetic field. And since it doesn't have a strong magnetic field, the sun is constantly stripping stuff from its atmosphere, and that's why it doesn't have life on it. And it's not blue and beautiful. It does have water on it, but the atmosphere is just crap, basically. Okay, so what happens with the solar wind? Now, solar wind is just made up of lots of different charged particles that are being expelled from the sun. We hear about magnetic storms on the sun and how it affects cell phone reception. What's happening is our satellites are in this magnetic field, and when that magnetic field gets pushed, they get exposed, and that can get in the way of your mobile phone reception. So these electric charged particles, they get caught into this magnetic field, and they will spiral until they get caught in the poles. And when they interact with our atmosphere, they start to glow. So this is where the aurora borealis comes from. So here's some pictures. We got the sun being pushed off, solar wind. The sun releases these things. We get solar flares, magnetic storms, all sorts of stuff comes off the sun. It gets trapped in our magnetic field, and then it spirals around the magnetic field lines in the opposite direction because they're electrically charged, and the magnetic field, right, 90 degrees, so it spirals around these things until it hits our atmosphere. When it hits our atmosphere, it interacts with those oxygen and nitrogen molecules and creates this very beautiful color. So each charged particle is going to create its own color, and that's how they get the different ones. Now, notice that the south magnetic pole is actually at our north geographic pole. It's kind of interesting. So your compass doesn't actually point north, it points south. So keep that in mind, is that any thing that can move that is attracted, so iron things can be attracted to magnetic poles, and they're going to line up with the Earth's magnetic pole, and they're going to go from north to south. So anything that's charged, if it's positively charged, it actually goes to the north pole, which is our south magnetic pole, and anything that's negative actually goes to the north magnetic pole, which is the south geographic. All right, videotapes and seafloor spreading. Now, you guys might not know what a videotape is, or a VHS. It's like this really big cassette with magnetic tape in it, and you put it in your VCR, and it used to play like your Disney videos when you were like 2. Actually, if you have any of these, I'm pretty sure tape death has already passed, so they're pretty much worthless now, so you just throw them out. But videotapes are made of magnetized ribbons. They have like stripes and the different orientations of the electrons. There's a laser inside your VCR that actually reads that and tells it what color to produce and what sound to make. The Earth's seafloor actually is striped with magnetic material. So as the magma comes up through the seafloor, it cools, and as it cools, it's going to cool with the same direction as the Earth's magnetic field. Now, if you look at the seafloor here, you can see that it's striped. Why would the seafloor be striped? So some of it says that this way is north, and some of it says that this way is south, or this way is north. North. Why would it be striped like that? Well, what does that indicate? No? Nobody wants to take a stab about something and I just kind of gave you the answer? It says that sometimes the Earth north is this way, and sometimes it's this way. So every once in a while, the Earth decides that it doesn't want to use this as north, it wants to use this as north. So our magnetic poles actually switch every once in a while, which is kind of weird. And I can't tell you when it's going to happen because that is about the different times that it has happened. I believe that we're up here. Okay. So this is what it's done over the last, hundreds of thousands of years. So it flips back and forth, and then it goes through really long periods where it doesn't flip at all, and then it goes to like super long periods where it doesn't switch at all, and then it goes back to flipping back and forth like every couple of years. So I can't tell you if we're due for one or not, because I don't know. They don't know. There's really no way to tell if we're in this period or this period because it just kind of comes on all of a sudden. So this is kind of what our poles look like right now. This would be the north magnetic pole. This is the south magnetic pole. And when it goes through a switch, you can have 5 or 6 magnetic poles all over the Earth. What would that mean for us? Well, because we don't really use compasses too much anymore, we use satellites and GPS, it probably is not going to change our life too much. Pigeons might kind of fly the wrong way for a little while, but they use more than just the magnetic compass in their head. They use visual and sound and stuff, so probably wouldn't mess them up too much. And I was talking to some scientists over at Florida Tech who actually study a lot of this, and they said that our magnetic field would actually probably become stronger when this happens, so we really don't have to worry about solar wind or magnetic storms or radiation effects, things like that. So we don't know when it's going to happen. We think we're due for one in the next 100,000 years. It's not really a big deal. It just means that when you use your compass, when this is happening, your compass is going to point at the closest south pole to you, which might be right here instead of actually south. And then once it actually does flip, sometimes it goes through this reversal and it doesn't actually flip. So it goes through okay, we're going to think about flipping. We're going to put 6 poles all over the Earth, and then it kind of settles down after about 100 years. But then sometimes it doesn't even switch at all. Sometimes it just settles down back to the way it was. So that's kind of interesting. If you want to read about that, I always like that. All right, I have 4 clicker questions for you today. Here is the first one. Which of the following statements is true about the magnetic strength of a bar magnet?